Everything that you see on your screen right now are just numbers. Videos, games, and even the frame you're watching right now are just numbers. They are not English or not plain images. And today in this video, we are going to understand how computer decodes these numbers and performs various operations on them. Hi everyone, my name is Orkoduti and this is the first video of the Class 11 Computer Science series. And by the end of this video, you will understand what number systems are, binary, hexadecimal, octal, and decimal number systems, and how to convert between them like experts. If you don't understand a part, please pause, rewind that part, watch it again, do whatever you want, but do not proceed without understanding a part because everything is linked with one another. And if you don't understand one part of the video, then the rest of the video is just useless. So make sure you do that. Now, before starting to learn about different number systems like decimal or binary, we need to understand what a number system is at the first place. To understand that, say a number 729, for example. What do you understand from it? Well, there are 7 hundreds, 2 tens, and 9 ones. So basically, the number can be written as 7 times 100 plus 2 times 10 plus 9 times 1. Now you may notice that 100 is just 10 square, 10 is just 10 to the power 1, and 1 is just 10 to the power 0. Now the same number can be expanded using the new powers of 10, that is 7 times 10 square plus 2 times 10 to the power 1 plus 9 times 10 to the power 0, and which equals 729. Notice something interesting? As we move from right to left, the power of 10 keeps increasing. You may ask, why base 10? Why not 11 or 9? We could have used any number, right? The reason is simple. In decimal number system, we have only 10 digits, 0 to 9. The number is also called as a base of the number system, which is 10 in our case. Various number systems have various bases. For example, binary has base 2, octal has base 8, and hexadecimal has base 16. Note that the base of a number system also denotes how many digits the number system has in total. Notice that how systematically we can use the multiples of that base power and then add them up to represent a certain number. That is fundamentally the concept of a number system. Now that we have understood what a number system is, let's proceed to our first number system, which is binary. Unlike decimal, which uses 10 digits, binary uses only 2, 0 and 1. That's it. 0 and 1, 2 digits, nothing else. So you might be wondering, how can just 2 digits represent everything? Well, that question of yours will be answered in the next video, that is about logic gates and computer systems. But for now, don't let curiosity kill the cat. Anyways, moving ahead, now just like decimal uses powers of 10, binary uses powers of 2. To understand, let's take an example. Say 1011. Just like decimal, here too, each number will get multiplied with the power of 2, starting from 0 and increasing as we go left. So 1011 can be expanded as 1 into 2 cube plus 0 into 2 square plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. And solving further, we get the value as 11. So in simple words, 11 is the decimal representation of binary 1011. And this is the exact process by which we convert a binary number into decimal. Let's take another example, say 10010. Do the same thing again, expand it using powers of 2 and then add them up to obtain the decimal representation. Now converting a decimal number into binary is a pretty easy one. You just keep dividing the number by the base, which is 2, and record the remainder in each step of the division. until you cannot divide anymore. And after you are done, arrange all the remainders in the reverse order, starting from the last one to the first one. Congrats, you just converted a binary number into decimal. Next on our list is octal number system. And as the name suggests, octal number system has 8 digits in total, starting from 0 all the way up to 7. So the base this in this case will be 8. Converting between decimal and octal is exactly the same as converting between decimal and binary, the process we just have done in the previous section of this video, except just use 8 instead of 2. For example, to convert 237 in octal to decimal, we write the following expanded forms using powers of 8 as previously done in binary and decimal, and then add all the terms together to obtain our decimal version of that number, which is 159. Interestingly enough, converting decimal to octal is also exactly same as binary, just that we need to use 8 instead of 2 to divide the number, and then keep dividing until we cannot, then collect the remainders in every division step in the reverse order of their arrival, and you have the octal representation of our number. By this point, we know that each place in octal system can be represented as a multiple of the power of 8, and 8 is 2 cube. This means one octal digit can exactly represent a 3-digit binary number. Let's try to visualize this. Let's take 110101. Now make groups of 3 digits from the right, and we end up with two groups, first one being 101 and second one being 110. Now convert each group from binary to decimal, and we get 6 and 5. So 110101 in binary is equals to 65 in octal. This way you can convert binary to octal directly. It is very natural to not understand this on the first go, so please consider rewinding and watching this a second time. Now let's proceed to hexadecimal number system, and as you expect, we have 16 digits here. 0 to 9 are the first 10 digits, and because we have run out of digits, we use A to F, that is 6 letters, to complete the 16 digits. Now here A means 10, B means 11, and so on and so forth until F, which is 15. Interconverting between hexadecimal and decimal is also similar to how we did it previously for binary and octal. Just expand using powers of 16 instead. To understand this visually, let's say we take a hexadecimal number 4C. Now just like before, we assign powers from right to left, and we end up with an equation 4 into 16 to the power 1 plus C into 16 to the power 0. But remember, C represents 12, so this becomes 4 into 16 plus 12 into 1, which is 64 plus 12, and finally we get 76. So 4C in hexadecimal is equal to 76 in decimal. Converting decimal to hexadecimal follows the exact same pattern we have already seen in octal and binary. We simply divide by 16 and keep track of remainders, and then rearrange them in the reverse order of their arrival to obtain our decimal number. Let's take 76 again. 76 divided by 16 equals 4, and the remainder is 12. Now 12 remainder represents as C, and we have already got 4 in our last division step, so the answer becomes 4C. Now here comes the interesting part. Just like we grouped binary digits in sets of 3 for octal, we group them in sets of 4 for hexadecimal. Why 4? Because 2 to the power 4 equals 16. So one hexadecimal digit can represent exactly 4 binary digits. For example, take the binary number 110110. Group from the right in groups of 4 digits, and we end up with two groups, 1100 and 1100. Now convert each group from binary to decimal, which is 12 and 12, and again we convert 12 to C. So 1100 in hexadecimal is CC. Again, consider rewinding this part if you could not understand it. It's a difficult topic, and do not proceed further without understanding the concept. Now we have explored all the 4 types of number systems in our syllabus, and to conclude, decimal uses base 10, binary uses base 2, octal uses base 8, and hexadecimal uses base 16. We learned how numbers are expanded using powers of the base and how conversions work by either building up values or breaking them down through division. We also saw some powerful shortcuts: binary groups of 3 for octal and binary groups of 4 for hexadecimal to directly convert between them without using decimal as the intermediate. And most importantly, we understood that binary is the language of computers. And this is just the beginning, because everything in computer science, data representation and logic building, programming, all of it stands on this foundation. No matter which number system we are using, the rules never really change. We either expand using powers of the base or reduce using division by the base. Different systems, but the same underlying logic. If you like this video, then please consider liking and subscribing. Also comment down below if you want a dedicated video on problem solving related to this chapter, and also what I could improve to make your experience better. In the next video, we will take this even further and explore how computers actually work with these numbers, what is the implication of binary number system, and how computers actually perform different tasks. And until then, keep questioning, keep exploring. Goodbye.